So my name is Amit Kumar, and today I am presenting this talk about GRB 221009A and the ultra-long gamma ray burst. And I start with the introduction of gamma ray burst because I already have a lot of done. So just a brief introduction. So GRB are the most bright object in the universe and discovered in 1967 by the Bareilly satellite. And they are isotropically distributed around the sky, and probably the emission come in like two phases. One is the prompt emission phase and other is the afterglow phase. And this is the fireball model which used to explain both the emission phases. And prompt emission phase occur within the jet due to some internal shock. And this is the prompt emission light curve, which can be any of the form. And this one is the spectra of prompt emission spectra, which is generally fit by a band function, which is non-thermal, and sometimes evidence of thermal component also seen. And these are the afterglow light curve. Is 5-component light curve in X-ray and 8-component light curve in optical. So, and origin from the when the fiber interact with the ISM medium. So now different kind of GRBs. Generally, GRB defined into two phases. One is the two part classes. One is short GRB, which has T90 less than 2 seconds. Other is long GRB, with T90 less than 2 seconds. But some authors also think there is other class of GRB, which is ultra long gamma ray burst, which has duration greater than 1000 seconds. So why 221009A is important to study the ultra long GRB? Because this has the duration greater than 1000 seconds as detected by the Fermi, but Swift so initially thought because it is too bright and lie in the galactic plane, so it thought it might be some galactic transient, and the initial detection was not there for Swift bat, but only detected in the afterglow phase. So I also observed this afterglow part of this GRB optical afterglow part with some Aries telescope in India, and 1 meter and 1.3 meter and 3.6 meter dot with optical NIR observation, and we present the afterglow light curve in other paper, which is led by Ruben, and also I am the corresponding author in that paper. And light curve was well followed by our group with different telescope around the world. So this GRB also very important when we combine the TV GRB to the ultra long GRB, because now there are 7 TV GRB with the 221009A is one of them, and it is the brightest ever GRB with the and also the most energetic GRB in with the 18 TeV photon have detected from this GRB also. So how I study the sample of ultra long gamma ray burst? I selected all the Swift detected GRB, and this is the distribution of how this work. The Swift detected GRB, Swift showing like a low sensitivity toward over the ear toward detecting the very long gamma ray burst, because the histogram shows in this a yellow or green or pink histogram shows that the detecting capability of ultra long gamma ray burst has decreasing Swift over the year, and now thankfully Swift SOM and EP has already begun detecting some ultra long gamma ray burst. And so how I decided my sample, I plotted all the sample GRB in which is a bimodal distribution, and some are the short GRB, which is not my concern in this case. And I plot only the long gamma ray burst with the Gaussian distribution. And I selected only those GRB which are greater than mean of this distribution, Gaussian distribution, and divided them into bronze sample of ultra long GRB, silver sample of ultra long GRB, and the gold sample of ultra long GRB, which has detects which are greater than 3 sigma of this distribution. So in this GRB, in all these GRB, I choose all the prompt emission light curve and run a machine learning code to how the prompt emission light curve different classes of GRB like bronze, silver, and gold sample are different from each other. So I found that the gold sample of GRB are lies in the one corner of the plot, which is shown by the pink, and some of the short GRB and other GRB are on the different it's showing some this bronze sample could be the different class of GRB than the other distribution of GRBs. So this is this is the one motive is showing that it can be different population. So next, if we plot the proper fluence of all this detected GRB, it's so fluence is increasing with the T90, but at the end of toward the ultra long GRBs, fluence is not very large, but due this fluence is spread over a longer time scale of these ultra long gamma ray bursts and can be make them ultra long GRB are faint. And for these faint GRB, these are only detectable at the lower redshift, because short GRB has the only detectable up to 1 or 2 redshifts, but ultra long GRB are also showing the similar because of the faint nature of this GRB. They are also detectable only at the lower redshift than the other long GRBs. So to search the progenitor of this GRB, what could be the origin of this ultra long GRB? So one thing is if there is a detection of supernova, but supernova was not detected in GRB 221009A with ground-based observation, optical observation, but GSW observation shows some a spectral signature of the supernova emission. But our observation do not show any indication of supernova at that time. So second method is to know the progenitor. So we can calculate the Bohr time of this GRB. This is one of the indirect method which is suggested by some Bromberg and Bromberg et al. 2011 papers. So we calculate the T Bohr time for each GRB, and if this T Bohr time is greater than the T9 duration of the burst, it has it could be from this collapsar origin, or otherwise it has some other origin, it can be merger or it can be shock breakout. So most of our GRB, we are considered GRB, has this collapsar origin. So second thing is to know what kind of central engine are governing these GRB. Central engine can be either a black hole or a magnetar. But magnetar has one limitation, that it cannot have the energy budget greater than 10 to the power 52 hours. So we calculate this we calculate the energetic of all the GRB, this if kinetic energy and isotropic energy in X-ray and in gamma ray, and compare that, and only few GRBs are have this energy greater than the energy budget of magnetar. So magnetar could be one of the possible central engine, and for this GRB only black hole engine is possible. And other method is to find the same energy of this GRBs, beaming energy. If I projected the observed energy by the Fermi telescope to the beaming angle, and then the energy if this corrected energy is greater than, and this one is the direct energy, this one is the corrected energy. If this corrected energy is greater than 10 to the 52, so it should be a black hole central engine, otherwise a magnetar is a possibility. So then I compare if environment could be the reason of this ultra long emission from this GRB. So we found that the environment is not very different of these GRB than the other long GRBs, and so the environment is not not responsible for this ultra long emission, and this may be due to the central engine activities. So after doing all these observations and this analysis, then I moved shift my known as to analysis to the simulation part, and I use major simulation code to simulate which kind of star producing this ultra long GRB. So ultra long GRB progenitor could be the Wolf-Rayet, could be the blue supergiant, or red supergiant is not a possibility, because that take too much longer time for this envelope to take to emerge from this star. So we evolve a different masses star in which choose some initial parameter like critical rotation and initial mass, and we simulate a different type of star, and we found that some low rotating, moderate rotating star could be the progenitor of these ultra long GRBs, which has the T free fall time is of the order of this GRB. Otherwise, the free fall time in Wolf-Rayet star could only be Wolf-Rayet can be a progenitor of typical long GRB, but for ultra long GRB, some blue supergiant star are the probable candidate of their progenitor. So this is the method how I calculate the free fall time using this formula from this paper, Perna et al. 2018, and our free fall time, our free fall time are comparable to this bore time calculated in this Bromberg et al. 2019. These are like quite comparable. So seeing this, our method is one like correct in finding this progenitor of these GRBs. And finally, this is the summary of my paper. So I will select this both GRB to study the ultra-long gamma ray burst and study the complete sample of ultra-long gamma ray burst, dividing them into bronze, silver, and gold subsample. So our gold subsample shows the some of the GRBs are due to like black hole central engine, and some satisfy the magnetar. And our also finding that the BSC star could be the progenitor of these ultra-long gamma ray bursts. So this is paper which I submit using all this analysis. So I appreciate if you go through this paper. And this is the future, because there is a recent GRB detected, and this is the first GRB which has detected in 4 episodes, B, C, D, and E. So this could be the another candidate of ultra-long GRB, which might be due to tidal disruption or different episode of single GRBs. So this is why.